Lecture 35 is the first of three lectures on optical properties of materials. In this lecture, we talk about the complex refractive index and optical constants. We talk about refraction and total internal reflection. And then we talk about the light conforming effect in optic fibers. Finally, we talk about the Fresnel equations. So the first student outcome is that you should be able to relate the index refraction to dielectric response of materials, and then relate the extinction coefficient to dielectric loss and absorption coefficient. When the light goes into a particular medium, the speed will be slowed down, and the ratio of how much it will slow down is determined by the index refraction, n. And the index refraction is really the square root of the dielectric constant. So all these things that we talk about in the dielectric behavior in the previous chapter can be applied here. The only thing you need to know is that now we're talking about optical frequencies. So with the slowdown of the light wave, the wavelength will be reduced by the same factor, index refraction as well, and the propagation constant or the wave vector will be extended. However, the photon energy remains the same because the frequency remains the same. So at optical frequencies, we only have electronic polarization contributing to the dielectric constant. But obviously at lower frequencies, depending on the material, we may also have ionic and dipolar polarization. So for materials that only have electronic polarization, the dielectric constant in the optical frequencies will be about the same as a dielectric constant at low frequencies, which is going to be the square of the index refraction, which is going to be at the optical frequency. However, for materials with either ionic or dipolar polarizations at low frequencies, then the low frequency dielectric constant will be greater than the dielectric constant in optical frequencies. So previously we also have learned that the dielectric constant may have an imaginary part in some cases. And that means that for the index refraction, now we have the complex index refraction, which also is going to have an imaginary part, and which we call that extinction coefficient. This extinction coefficient is related to the absorption coefficient. Through this formula, they are proportional to each other, kappa and alpha. And obviously alpha, as you remember, we have the Beer-Lambert law, which governs the decay of the light intensity as a wave is propagating through that medium. So in materials where the extinction coefficient is 0, then we have 0 absorption coefficient, or the imaginary part of the dielectric constant is 0. Then there's no loss of energy. That means that medium is actually transparent to the wavelength that we are considering. So for the second student outcome is that you should be able to use Snell's law to calculate the refraction angle and to determine conditions for total internal reflection. So the Fresnel equation, the Snell's law governs the direction of the reflected light. For the reflection, it'll come out at the angle as the same as the incident angle. The angles are all measured from the normal direction. For the refraction angle, it's dictated by the index refraction differences across this interface. So the Snell law is n times sine theta is a constant across this interface. So now the issue is that if M1, the first medium, has a greater index refraction than the second medium, then we may have a situation that at some point, as we call critical angle, the exciting angle theta 2 may be at 90 degrees. If the incident angle is greater than the critical angle, then we don't have any light going into the second medium. We only have the light reflected back. This is so-called total internal reflection. So the third student outcome is to use the Fresnel equation to calculate the reflectance and retransmittance across the interface, especially at normal incidence. So for light reflection at the interface, the reflectance, or the percentage of light that is reflected, determines on the polarization direction of the incident light wave. There are two different polarization directions because that polarization of the electric field is perpendicular to the direction of propagation. So we have either the so-called S polarization, which is the situation when the electric field is perpendicular to the incident plane. The incident plane is formed by the incident and the reflected light. So for the S wave, the electric field is perpendicular to this plane. It's oscillating in and out of this plane. And we also have a P polarization, in which case the E field is in this plane. So it's actually oscillating as I'm showing here with the arrow. So for these two different polarizations, the reflectance may be different, okay? And then if the light is not reflected, then it'll go through it. We call it, in that case, it's transmit through that interface, so we can determine a transmittance. So the reflectance and the transmittance across this interface, the sum will be 100%. And obviously, both the RS, the S wave reflectance, and the P wave reflectance do depend on the incident angle. At 0 degree, they are degenerate. They have the same value, but as the angle goes up, as you see, eventually both of them will go to very high values. 90 degrees, it's basically everything will be reflected. But there is some difference between the S wave and P wave behavior. For the P wave, at some angle, the reflectance may go to 0, so nothing's reflected for the P wave. And for normal incidence, the RS and RP are the same, and they will be reduced to a very simple equation as I'm showing here. And so if you look at the light incidence for visible light on the glass surface, and in that case, the index refraction for glass is about 1.5, you get about 4% reflectance. That means 4% of light will be lost on the front interface when light goes into the glass, but obviously when light goes through glass, there's also a backside which will lose another 4%. That means overall you're going to be seeing only 92% of light going through, even though there's no attenuation of the light wave inside glass. Glass is transparent. So this is the end of the review for this lecture.